Hello everyone, Mr. Fawcett here, and we're back with another geometry lesson. Today we're going to look at compound events and how to find the probability of them occurring. There are two specific types that we're going to look at, mutually exclusive compound events as well as inclusive compound events. We'll talk about what makes one fall into one category versus the other and the differences in the formulas for finding probability. But before we really get into the nitty-gritty, let's look at a simple introduction problem. It says, if a wheel is spun, what is the probability that a number less than 3 comes up? So a number less than 3. Well, we're assuming that each of these sectors on the wheel are equal in area and symmetrical, so that the probability of landing on one number is the same as landing on any others. And there are two favorable outcomes for us, right? If we're trying to find a probability here, theoretical probability, favorable outcomes over total, 1 and 2 are both good for us, right? So 2 favorable outcomes over 10 total. So our probability is 2 out of 10. We could also write that as 1 over 5, 0.2. But this is what makes this a compound event, right? Because this is an example of a compound event. If we have more than one desired outcome or more than one favorable outcome, we have a compound event, right? I purposely didn't simplify this here to 1/5 because I didn't want to confuse you, because now this numerator is 1. But before we do any simplifying, if the number of favorable outcomes is more than 1, then it becomes a compound event. If the number of favorable outcomes is 1, then we describe that as a simple event. That is where it describes a single outcome. So today we're just going to focus on the times where there are more than one favorable outcome for us during an event. So compound events, an event made up of 2 or more simple events. Now the first compound event that we're going to talk about, or the first type of compound event, is a mutually exclusive events. These are events that cannot happen during the same trial of an experiment. And we'll look at an example below, but let's say I had changed the example up here, and let me get rid of this. But let's say instead of a number less than 3 coming up, I add on to this a little bit, and I say that a number less than 3 or a number greater than 4 comes up. So I just added on some pieces here. Well, obviously, we've just given ourselves more desirable or favorable outcomes, right? Now we can also land on a number greater than 4, and we're happy. Well, if I quickly look at that probability, there are 2 numbers, so favorable over total. Stay organized here. 2 numbers less than 3. And there are 6 numbers greater than 4, right? 5, 6, 7, 8, 9, and 10. 6 numbers. So 2 plus 6, still 10 possible that will work. We can also put the slashes on 1 and 2 because those are also favorable. So we end up getting 8 out of 10. Now, for a compound event to be considered mutually exclusive, it means that any of these 8 desirable outcomes cannot be one and the same, right? So I can't have a number that's less than 3 and greater than 4. There's no way for the same number to count for both categories. Each of these 8 desired outcomes are standalone, right? If one of them occurs, another one will not occur. If a 1 comes up, well, that means that a 4 is not going to come up. If a number less than 3 comes up, well, that means a number greater than 4 is not coming up. So this is what we mean by mutually exclusive. It means that any of the simple events that the compound event is made up of, or any of the outcomes, do not overlap with each other. And it'll probably make more sense when we talk about inclusive events, and we do talk about the overlap. But mutually exclusive events, they're made up of outcomes or simple events that cannot happen at the same time. Let's look at the notation here. So mutually exclusive, the probability of two mutually exclusive events A or B occurring is the sum of their probabilities. So the probability of A or B is equal to the probability of A plus the probability of B. You also may see this written like this. The probability of A union B. All that this means is A or B is equal to the same thing, just a different notation. So that little U shape, if you see that, that means probability of A or B. If we think back to probability of A and B, well, that's the probability of A times the probability of B. I don't think I put this in the video. I think we just talked about it in class. But we could also write it as the probability of A upside down U. So this means the probability of A and B occurring. So again, same formula, just different notation here. And this is just something you have to memorize. I guess one way that you may think about it, if you think about this as an N, well, if you're thinking about the probability of A and B, or the probability of A or B, A for and comes before or in the alphabet, and N comes before U. So you could think about, okay, do I use the U or the N? Well, if I'm doing A and B, A comes before O, so I'm going to use the N because that comes before U. But otherwise, you can just memorize it. We kind of already talked about an example of a mutually exclusive event, or rather event, but we'll throw another one in here. We'll say rolling, and we're talking about a die, rolling an even number or a 3. Right? Those could not happen at the same time. If you roll an even number, you're not going to roll a 3. And if you roll a 3, you have not rolled an even number because 3 is odd. Let's look at a quick example of calculating this stuff before we do inclusive. So let's jump down here to number 2. It says a blood truck comes to campus to collect donations. However, they only need type O and A. A student has a 9/20 probability of being type O and a 2/5 probability of being type A. Are the events mutually exclusive or inclusive? Why? Well, I'm choosing this because they're mutually exclusive, but you can tell me why. And part B says find the probability that the student is able to donate. So pause the video, see if you can answer parts A and B, and then we'll go over the answers. Okay, so for part A, right, these are mutually exclusive because a student cannot have both blood types at the same time. They're either going to have O or they're going to have A. Now, I think there is this extremely rare circumstance where you can actually have two different blood types, but for all intents and purposes, you either have, well, there's more than two blood types. There's more than A and O. We have B and we have AB. But essentially, you've just got one out of those 4 blood types. So if we know that these are mutually exclusive events, Well, our formula up above said we just add the probabilities together. We'll call this A, and we'll call this B. So the probability of A or B, remember we could write that as probability of A or B, is equal to 9/20 plus 2/5. 9/20 plus 8/20, to keep that common denominator, gives us a probability of 7/20, or 0.85. Okay, let's go ahead and look at inclusive events now, where there is some overlap. Okay, so inclusive events. These are events that have one or more outcomes in common. This means that they can occur in the same trial. So an example would be like having a die and saying, I want to roll either a 1 or an odd number. Well, because 1 is also odd, some of your outcomes will overlap, right? You have a favorable outcome for 1 because you want to roll a 1, and then you have favorable outcomes of 1, 3, and 5 based on the odd numbers. But notice that 1 is a part of both categories. So working out these probabilities is a little different than it is for mutually exclusive events. So inclusive events in words, the probability of two inclusive events, A or B, occurring is the sum of their individual probabilities minus the probability of both occurring. So as far as notation goes, probability of A or B, again, given they're mutually exclusive, is the probability of A plus the probability of B minus the probability of A and B occurring. So you have to subtract off that piece of overlap. Let's actually show you an example. So we will say rolling a 1 or odd number. Well, again, if we look at the different categories here, rolling a 1, favorable outcomes are 1, right? The number 1. Odd number, well, we've got 1, 3, and 5. So we can see that there's this overlap, right? 1 counts for both. Rolling a 1, I guess I should put that there as well, and for rolling an odd number. So if we set this up, we will call this A, this B. Probability of A or B is equal to the probability of A, well, that's 1 out of 6, plus the probability of B, well, that's 3 out of 6, minus the probability of A and B happening at the same time. Well, the only time that rolling a 1 and an odd number would happen is if you roll a 1, right? So that's going to be 1 out of 6 times. And we're going to subtract that. So we have 1/6 plus 3/6 minus 1/6. That gives me 3/6 or 1/2 or 0.5. So the probability of rolling a 1 or an odd number becomes 1 out of 2. Now, this example was really straightforward, right? Because we only had 6 outcomes to compare. So you really could have figured this out without the formula. Some more complicated examples where there's a lot more outcomes, it just makes sense to use the formula rather than just think it through intuitively. Let's look at one example for inclusive events, and then we'll wrap the video up. We're going to go down here to the soccer and lacrosse team problem. So go ahead, pause the video here, read through both parts, A and B. Think about whether they both deal with simple events, compound events, mutually exclusive compound events, inclusive compound events, and then think about what formulas we need to use to find the probabilities. Then come back, join us. We'll go over the solutions, and we'll be out of here. Okay, so it says, of the 200 girls in the school, 20 played on the soccer team and 50 played on the lacrosse team. There were 8 girls who played on both teams. Well, part A says, find the probability that a randomly chosen female student played on both teams. Call that event A. So the probability of A, well, there's 8 girls who played on both teams, so our favorable number of outcomes are 8. There are 200 total female students, so 8 over 200. Oh, we can simplify. If we divide everything by 8, we get 1 out of 25, or we can say 0.04. Either of those would be acceptable. That would be the probability of choosing a female student that plays on both teams. That was pretty straightforward. If we look at B, though, it comes a little bit more complicated. It says find the probability that a randomly chosen female student played on either the soccer or the lacrosse teams. Well, first we need to decide, is this a mutually exclusive compound event, or is it an inclusive compound event, where the outcomes can overlap? Well, because there are 8 girls who played on both teams, this is an example of inclusive events, right? Because you can be on both the soccer and the lacrosse team. So we have to remember to subtract off that overlapping portion. So let's say the soccer team represents A, or the probability that they're on their soccer team, and the probability that they're on the lacrosse team represents B. So the probability of A or B is equal to the probability of A, which is 20 over 200, plus the probability of B, which is 50 over 200, minus the probability of A and B occurring at the same time, which would be 8 over 200. So we have the probability of A plus the probability of B minus the probability of A and B. Well, 20 plus 50 is 70, minus 8 is 62, so 62 over 200. We simplify, we get 31 over 100, or we could also write that as 0.31. So the probability of picking a female that plays on either team would be 0.31. Okay, that's going to do it for this lesson. We'll get some more practice in class, but until then, enjoy the rest of your day, and we will look forward to seeing you next time.